classical mechanics problem. I kind of modified this from one that I found online. So let's just get to it. So the goal is you have a box. It could be a person. Let's say it's a person on a cardboard sled, and you want to pull them and find out what the maximum acceleration of the person would be. What angle would you pull to give them a maximum acceleration? That's what we want to find out, and that's what we're going to do. And we will do this. I will do this two ways. Number one, I'm going to do this as a max-min problem. That's going to be awesome. And then number two, I'll do it by graphing, and we can look at the maximum acceleration. Let's just get started. Okay, so of course this is a Newton's second law problem, meaning that we have the net force is mass times acceleration. Okay, so if that's the case, I need to first draw the forces on the object. So here's my object. I have the downward gravitational force mg. I'm pulling with some force. I didn't specify what that force was. Notice I did not specify that. This is my x-axis, theta. Then I have a normal force N, and then I have a backwards pushing friction force F friction. And I want it to accelerate that way. I can write Newton's second law in two components. I can say the net force in the y direction is 0, right? Because if the object does not accelerate in the y direction, then the forces have to add up to 0. So let's go ahead and write that down. This is a theta. What forces do I have in the y direction? Well, I have the normal force. I have this component of the friction, the force I'm pulling with, which I don't know, and the gravitational force. So that'd be N plus F sine of theta minus mg equals 0. Okay, now I'm going to need that because I'm going to need the normal force. In the x direction, I can say F net in the x direction is, what forces are there? Well, I have a component of the force. This is the adjacent side, so it's going to be the cosine, F cosine theta. That's it, that force. And then I have the frictional force in the negative x direction. I'll put that as minus F, and that's equal to mass times acceleration. In the x direction, it's going to leave it as A, just to make it simpler. Our frictional force model says that the frictional force, the magnitude, is going to be equal to the coefficient of kinetic friction times the normal force. That's kinetic, because it's sliding. So if I know the normal force, which I can get up here, which is just going to be equal to negative plus. Yep, and then I substitute that in down there. I can write this whole thing as F cosine theta minus the frictional force, which is mu k, times the normal force, which is, I'm just going to multiply it out, F sine theta, mu times the normal force is negative, so it's going to be plus. And then I have mu times mg. Where did I get the minus sign from? Oh, it's this minus. So minus the negative. So minus mu k mg equals ma. And then I can divide by m. But let's write this as F over m times cosine of theta plus mu k sine of theta minus mu k g equals A. So now I have A as a function of theta, right? Yeah, it depends on the force, it depends on the mass, but it also depends on theta. So as we change that angle, we want to find out what angle gives us the greatest acceleration. So there's my A as a function of theta. I'm going to write that up here because it's very important and useful. A as a function of theta, F over m cosine theta plus mu k sine theta minus mu k a g. Now, let's just double check, right? Because we want to make sure things have the right units. So this F over m has units of acceleration. That does not have units. 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 And that's newtons per kilogram, which is meters per second squared, same thing. Okay, so it has the right units, so that's good. Now, what angle could I pull at to give myself the greatest acceleration? Well, we could imagine that as I pull, there's some maximum value of acceleration or minimum. We don't really know for sure, but it's going to be a maximum. And if I want to find that location of that maximum, just imagine that I had a graph of a as a function of theta, and it goes like this. Well, what's true at that point up there? That's true is that the slope of the curve is 0. So I can find the slope of the curve by taking the partial of a with respect to theta and setting that equal to 0 to find that critical point. That critical point is going to be the maximum. We could prove that, but I don't think I'll do that. So let's just take the partial of a with respect to theta. The partial of a with respect to theta. Well, right here, I have f over m as a constant. That's not a constant. So I'm going to write this as f over m, and then I'm going to take the partial of cosine theta with respect to theta is negative sine theta. And I don't have to take the derivative of theta because it's the partial of theta with respect to theta is 1. Okay. And then over here, I have plus mu k times the cosine of theta, right? I take the derivative of that with respect to theta. And then I take the derivative of mu k g. It doesn't depend on theta, so that's 0. So that's it. Now I'm going to set that equal to 0. So this is a constant. I can multiply both sides by m over f. I get negative sine theta plus mu k cosine theta equals 0. Now add that to both sides. Mu k cosine theta equals sine theta. Now you might think, oh my goodness, how can we solve for theta? Because if I take the inverse of this side, I'm going to have a theta over here, but I'm still have a theta over there. It doesn't get rid of the theta. You know what to do. There's a trick here, right? The trick is to divide both sides by cosine theta. So I get mu k equals sine theta over cosine theta. And I don't remember a lot of trig functions. I don't remember a lot of trig identities. But I do know that sine over cosine is tangent. Now I can find the value for theta by taking the inverse tangent of both sides. Theta, and this is theta. This is not theta. This is not the maximum theta. This is the theta with the maximum force. So theta is maximum acceleration is equal to the tangent inverse of mu k, which you can do, right? Because mu has no units. You can't take the inverse tangent of something with units. It has to have no units. That's that. So let's put that up over here. Theta equals inverse tangent of mu k. Now, if you wanted to, you notice we only get one angle. So it'd have to, I mean, logically it'd have to be a max. It could be a min, but you know what the min is, right? Let's just check this function really quick. Because what if I pull straight up? What would the acceleration be? Please say the acceleration is 0. So it should be, right? So cosine of pi over 2 is 0. And then, oh, it's not going to really work. Okay, let's not do that. Let's just check this the other way. So what I want to do is to take this function and plot this function as a function of theta and just see if we get this for the maximum angle. And that's what we're going to do in Python. And I think it's a really useful way of solving problems because sometimes you may not be able to take the derivative or it might be very difficult. So plotting that can give us an idea of whether we're right, and then we'll stop after that. Okay. Now, if I want to plot this, I do need to have values, right? I'm going to do a numerical plot. So I have the mass, I have mu k, I have g. I do need to pick a value for theta, for f. And let's just pick, and hopefully it works out. F is 100 newtons, but then we can change that. So this will give us a chance to practice making functions in Python. That's what we're going to do. Okay, jumping over to Python. Here we are in Python. I've already got started up. We're obviously going to need a graph, so I'm going to make that G1 graph. Title equals pulling acceleration versus pull. I don't know, that makes sense, that's fine. X title is going to be equal to theta. I like to plot this in degrees. I think better in degrees. I don't know about you, I think better in degrees. The Y title is going to be the acceleration in meters per second squared. And then I'm wrapping it around just so it fits. The width obviously has to be small, 400. Height equals 200, just so the graph plots. Now the thing I'm going to plot is going to be a G-curve. Color equals color dot blue. Okay, now I'm going to enter my constants. M equals 45, mu equals 0.4, F equals 100, theta equals 0. I need to have an angle to pull with, so I can change it. So I'm going to start at theta, and then how much I'm going to and that's in radians. How much I'm going to change that by, d theta. Let's just pick 0.1. It doesn't really matter. Okay. I want to make a function that I give it both the force and the angle, and it returns the acceleration. That's what I'm going to do. And so I'm using a couple global variables. I'm using a global coefficient of friction, even though let's pass that in there too, because it'd be fun. And the mass, I'll leave the mass as a global. So to make a function in Python, we just say def, and then we give it a name. And I'm going to call it a because it looks like a function. And then I need to say what variables am I going to pass to that. And they have to be fake variables, right? I don't want to double use my names. So I like to use t in front of the name I want to use for temporary. So I'm going to give it a temporary theta, t theta. I'm going to give it a temporary force, t force. And then I'm going to give it a temporary coefficient, t mu. That's just what I do. You know, everyone does things their own way. That's the way I do it. Now in this space, t theta, tf, and t mu are whatever I pass to them. So let's calculate the temporary acceleration. I call it at, surprisingly. And I'm just going to enter my function up here. So I have f over m, that's for f tf over m, right? And mass is a global thing, times cosine, I'm looking up here, of theta, so it's t theta, plus t mu times sine t theta. And then I have minus mu k times g. So minus t mu times g. G is a global. That's my thing. And I'm going to return at. So let's just see if it works. Print a of, let's say, pi over 4 for my angle, 100.4. Let's just see if it works, right? Let's just see if it works. If it doesn't work, then we need to do something. And it didn't work. Why titles? Okay. That's a funny reason to not work, because I can't type. Why title? I did S. That's weird. Another error. Can't find G. Didn't put it in there. G equals 9.8. Okay, negative. So that's a problem, right? That says that maybe my force is not large enough. Let's just put this at 150 and let's see if that fixes it. No? Okay, so that means I have an error. Good thing I text TF over M cosine theta plus T sine theta minus mu k times G. Huh. Let's try that a little bit bigger. Oh, I know what I did. I did this as 150. I had this at, no, maybe not. Let's just try this at 250. Because if the force is not great enough, it's not going to be enough to overcome friction. It's still negative. A pi over 4, so 45 degrees. The force, oh, that's why. I wasn't changing that. Okay, so it's smaller, so that's the problem. I just need to have a bigger force. 200, I think, should be enough. Yeah, so what was happening is if the force is too small, then the frictional force is going to be greater than the horizontal force of that you're pulling with, and it's actually going to accelerate the other way, which wouldn't happen but we already predefined the acceleration to be in that direction. So I think it's going to work now. Now, we don't need that. I'm going to make a loop while theta is less than pi over 2, right? So I want to go from pi 0 to 90 degrees. I want to plot theta versus acceleration. So I can do that all in one step. F1 dot plot the angle theta and the force A of, now I'm looking right here, what order do I need to put that in? Theta, F, mu. Now I need to increase my value of theta. Theta equals theta plus d theta. Let's see what happens. And there we go. Okay, so, I plotted theta as, I want to plot theta times 180 over pi, so it's in degrees. There we go. Okay, so from that, I get a maximum acceleration right around here, 20.3. Let's just print it out, what we calculated analytically. Print theta for max A equals A tangent of mu, and that's in degrees, so I'll multiply that by 180 over pi. $21.8, that seems legitimate. 21.8. It's hard to tell really. You can get a much better value. I could only plot this region right here, and that would make it zoom in a little bit better. Let me show you another really quick trick. If you're dealing with numerical calculations and you want to look at the graph in more detail, here's a trick. Up here under the graph, I can say fast equals false. And when I do that, it uses a different engine to plot the graph. And in this case, I can actually zoom in. You can scroll, zoom in like that. So it makes it a little bit easier to find out where the max is. And you can see here, you can actually see the data points, right? Because there's a data point and there's a data point. So I need a smaller d theta to really get at it. But that is just a way to think about how you do these max-min problems, and two ways to think about it. So practice with their Python stuff is useful. Hopefully that's helpful. Talk to you later.